Hello. Is this working? Yeah. Hi. Thanks for coming to my talk. My name is Marcelo Vanzin. It's almost invisible there on the slide. I'm a software engineer at Cloudera. I work on the Spark team. I'm also a Spark committer. And today I'm going to be talking about how to secure Spark applications and how to use Spark in a secure Hadoop environment. So basically, what is security? Security is a lot of things. It involves a lot of things. So it can involve everything from processes in your company to like give people identities and password policies, how to code your software so that the software respects security rules, and many other things. And here we're going to be focusing on three things that affect Spark directly. Which is encryption, authentication, and authorization. And you might ask, why do you need security? So basically, if your company has a need to identify users so that you know what those users are doing with your data, if you need to isolate applications so that applications run by different users cannot see what each other is doing, if you have data that needs to be protected and needs strict access control enforcements, or if you have a government like the US government who likes to create laws with very cute sounding names like SOX and HIPAA, which are really, really big terms of regulations, then this is something that you might need in your company. And before we go further, before you even start talking about securing Spark itself, you need a security environment where Spark will be able to inherit some of the security features. So first of all, as with all of the rest of Hadoop, you need to set up Kerberos. At Cloudera, we use HDFS, but any secure file system that integrates with the rest of the Hadoop stack will also work. You need to use Yarn for Spark in particular because that's the only backend in Spark that currently supports security. And of course, you need to configure all these different services to use security. So you need to configure HDFS and Yarn to encrypt data and to provide proper authentication and talk to Kerberos. And these three services provide the backbone for Spark to be secure and to respect your security policies. So first, let's start with encryption. So basically, in a secure cluster, you do not want data to be visible just by like hot linking something into your wires. You need that data on the wire to be encrypted so that it's difficult to have access to it. And some people also have a very strong desire to have at-rest data encryption so that even if you somehow have to dispose of your hard disks and someone gets hold of that, they can't get to that data. This is really very, very important to financial and government institutions. They're the people who come directly to us all the time asking, is this feature there yet? Is this supported? But basically, anyone who needs to deal with sensitive data will at one point have to deal with all these things that we're going to be talking about. So first, before we go into the details of how security is involved in Spark, let's look at what a Spark application looks like to see what's going on. So I'm simplifying it a lot, but generally you start a driver. The driver will start a bunch of executors. And there's this communication that happens between the drivers and the executors. So instructions that the driver sends to executors send state back to the driver, send results from tasks back to the driver. And all these control messages go over the wire. There's also a file download service so that files are distributed from the driver to the executors dynamically as needed. Oops, wrong button. The executors talk to each other to transfer shuffle blocks and cached blocks also. And in case you're using an external shuffle service, which here is simplified to be just one, but it's basically one instance running on every node of your cluster, the executors also talk to this shuffle service to send metadata about available blocks and to fetch blocks from remote nodes when needed. The executors also write to the local disk. Basically, they write the shuffle files to the local disk and then tell the shuffle service where those files are. And finally, you have the Spark UI, which runs inside the driver. And some people also requested that be encrypted. even though it doesn't really provide any sensitive information at the moment. So what was the state of the world prior to Spark 1.6? So there was SSL available for some of these RPC channels. There's SASL-based encryption for the shuffle mechanism in Spark. There was nothing available to encrypt the user UI, which also affects the REST API. And if you wanted to encrypt the data at rest, basically the spilled files and the shuffle blocks, you needed to use an encrypted file system underneath, which for some people is not desirable because they would need to redeploy their whole cluster. So just as a side note, so what's wrong with SSL? And there's really nothing wrong with SSL, except that in a distributed environment, it's really hard to manage. So basically, you need certificates to be readable on every node. And if you don't want users to be sharing certificates, which makes them not really that secure, it becomes really complicated because you either need to set up things so that every user has a certificate on every node, and Spark doesn't really have a very good way to be able to differentiate these certificates. And there's also issues with certificates being tied to certain hosts, and you can use a wildcard domain, but it has limitations. So there's all sorts of things that do not work well in a distributed system where you want things to work as transparently as possible. So in Spark 1.6, there was a lot of work done to replace some of the backends. So basically, all the RPC now is done on a new transport library that replaces the old Akka-based RPC. The HTTP file service was also replaced with some code that runs on this new transport library. And the transport library, which is the same one that was used for Shuffle, uses SASL for encryption. There's still no support for HTTPS on the web UI. The Shuffle files spilled to disk still require file system level encryption if you want to encrypt data at rest. And SASL in the JVM is still a very old implementation that uses triple DAS as the encryption algorithm. It's not bad, but it's getting old right now, and there are very better options these days. But right now, I think what the slide doesn't say, and it's basically the biggest drawback of using SASL is that it's slow. The API in the JVM is still based on old java.io APIs that require copying a lot of data around, and that makes enabling encryption drop the performance of your application a lot. In Spark 2.0, a few enhancements will be available. So the classes generated by the Spark shell, the REPL, are also going to be distributed using this new transport library. In fact, if you use CDH 5.7, which is based on 1.6, you can get this feature right now. There's also HTTPS for the web UI and the history server. This doesn't fix any of the issues with SSL we talked before about certificate distribution and per user certificates. But if you really want, you can enable SSL on the web UI. And there's work being done, mostly by our friends at Intel, to enable at-rest encryption for the shuffle blocks. This work depends on a third-party library called Chimera that Intel wrote. It's based on the encryption code that was used in HDFS. And the reason why this work is not checked in yet is that it's being added to the Apache Commons project, so it's going to be part of the Apache group of projects. And once that's done, we're going to modify the current code in Spark to use the Apache library instead. And one nice thing about this library, since it makes so much easier to use encryption, it's basically a nice, easy-to-use wrapper around the Java encryption libraries and also OpenSSL if you really want performance. The nice thing about it is that we can use that same library to replace the SASL encryption backend easily and get much better performance out of it, and at the same time upgrading to newer algorithms like AES. So that was the current status of encryption. So let's talk a little bit about why you need authentication and what is complicated about authentication in a distributed system. So basically, Spark, like the rest of Hadoop, relies on Kerberos. And if you're not familiar with Greek mythology, Kerberos is that cute three-headed puppy there. It's in Greek mythology, it's the guardian of the gates of the underworld. And I'm sure that the people who created Kerberos wanted that to be the analogy. what I like to think as a better analogy related to this other guy, Hercules. His last labor was to capture Kerberos and bring, and bring him back. And basically, dealing with Kerberos makes you feel like you should be Hercules because it's a very big struggle every time you have to do anything. So how does Kerberos work? This is a very big simplification of how it works. So basically, a user tells the KDC, the Kerberos domain controller, hey, I'm user Bob. And the KDC checks the user's password or whatever form of authentication is used and says, OK, Bob, here's your ticket granting ticket. This is the ticket that's going to allow you to access any Kerberos-enabled service in your data center. So when your application running as your user Bob wants to access, for example, HDFS, it goes back to the KDC, presents that ticket granting ticket, and says, I want to talk to this other service, HDFS. And then the KDC gives you back a ticket that you can use to talk to HDFS. And HDFS knows how to read that ticket and make sure that, and because that ticket is signed by the KDC, it knows that you are really who you are saying you are. So what changes with a distributed application? So you have your KDC happily serving authentication information, and now you start a Spark application. And an executor comes and says, I'm Bob, give me a ticket. And another comes, says, I'm Bob. And more executors are showing up saying they are all Bob. And at that point, the KDC starts thinking that something might be going wrong. It might be under attack, or user Bob might be compromised or something. And what happens is it starts denying authentication requests, and your application doesn't work anymore. So basically, Hadoop created a different way of authenticating using Kerberos to work around this KDC limitation. So basically, in Hadoop, your driver program will talk to, for example, in the HDFS case, the name node and request a delegation token. The driver is the only node that needs to talk to the KDC. It gets a delegation token from the name node, and it manually distributes those tokens to the executors. And the executors can use that delegation token to talk to any HDFS-related daemons in your system. So that avoids the KDC, except for that only node. And since there's only one node talking to the KDC, everything works fine because the KDC will not think it's under attack. Delegation tokens have many of the same problems as Kerberos tickets themselves. Mainly, the main problem being that they have a fixed time to live. This is OK for most batch applications. Delegation tokens can live at maximum for 7 days in Hadoop by default. And it's really rare for a batch application to live for that long. But lots of Spark applications, especially things like streaming, are meant to run 24/7. So having to restart them every 7 days is sometimes not an option. What was done in Spark 1.4 is that Spark itself can handle your delegation tokens by handling your Kerberos login, so that at the end of the 7-day period, it can create new delegation tokens, not renew them because it cannot after that period. There are current limitations, and the main limitation is that currently there's only full support for HDFS. There's limited support for Hive and HBase, in that Spark will fetch delegation tokens for those services, but it will not create new ones after the 7-day period. So after the 7-day period, if you're using Hive or HBase and Spark, you'll have to restart your application. And another limitation is, what about Kafka or other services that use Kerberos also and might have authentication? I'm going to single out Kafka here because that's the next thing that's coming up in security in Spark. And basically, Kafka adds security features in 0.9. It requires some changes to use some new APIs that were added, and that work is being tracked in Spark. And one problem with Kafka 0.9 is that it does not support delegation tokens. There are two ways of talking to Kafka from Spark. One way is the direct connector, which I'm not really familiar with the Kafka support, but there are two different ways. One is a single executor talks to Kafka, and in that case, you can get away by like doing a Kerberos login manually and getting the ticket granting ticket that allows you to talk to Kafka directly. But the really scalable solution using Kafka requires many executors to talk to Kafka brokers. And in that case, you go back to that problem of many people trying to log into the KDC and you being locked out. And until Kafka supports delegation tokens, we cannot scalably support Kafka in Spark. For authentication, that was it. Now let's talk about authorization. And this is not really related to Spark as much as in how do I make sure that a Spark can access my data in an environment where I have all these access restrictions in place. So authorization deals with how can I share my data with other people. If you think about the simplest form of authorization, it's file permissions. It's the thing that every computer user gets introduced to when they start using computers. So things Unix style user group, other access controls, or more featureful ACLs, for example. They're really simple, but they're high maintenance. For example, in Unix, you need to mess with umask if you need some automatic form of setting permissions. And that's very, very basic. Otherwise, you have to manually change every file that you create so that it has proper access controls. And the last bullet is the important point here is that you need a trusted entity to enforce these permissions. In the case of Unix file systems, the trusted entity is the OS kernel. If your OS kernel is compromised, you cannot trust the access permissions anymore. So the real problem with applications like Spark is that applications built on top of Spark is that they need more than just file system semantics. So if you start thinking about Hive tables, for example, you have tables, columns, partitions, and all sorts of different things that are not files and directories. And you want to be able to control access to those at that level, not the underlying files where those things are stored. And as before, you need some kind of trusted service to enforce these controls. You cannot trust the user to police himself and not access things that he should not. So if you think of a trusted service, it would be Hive. Hive has the Hive Server 2, which is the entry point to everything that Hive provides. A client talks to Hive Server 2, sends SQL queries, and Hive Server 2 gets all the metadata about that query from the Hive metastore, does all the access control checks, making sure that the user who submitted the query has access to all the things he requested. And then finally, it submits a MapReduce job, for example, to go and look at the actual data on the data nodes and then finally return the data to the user. Spark is an untrusted application because you have user code directly getting the metadata from the Hive metastore. And with that metadata, it has the location of the files and it goes directly to the file system, and it's, in this case, HDFS, to look at the data. This doesn't work because if the user has only access to portions of that data stored in the file system, there is no way to control that in this environment. But can you go at least a little bit towards that goal without changing Spark or the file system? So there's this project called Apache Sentry that provides role-based access control to different resources. It's mostly used by Hive today. And it integrates with the metastore server and Hive Server 2 to control access to Hive data. And it provides really fine-grained, you can set up like column-level access controls. And the nice thing is that it has an HDFS plugin that synchronizes file permissions on the file system with the permissions of Hive tables set up in the metastore. So basically, if you give a role permission to read the table, it sets up an ACL in HDFS that allows all users who have that role to read the table's files. If a user has a permission to create a table, it means the user can create a directory in the database's directory on the file system. So the problem with this is that it's still restricted to this file system view of everything. If you have something that does not map to a file or a directory, like for example, you want to provide column level and row level access control, you cannot do it with the Sentry plugin. It's basically a whole table or nothing approach. Still, you deploy it, and there's still some level of access control that you can provide to your users. So let's give a simple example of what I'm talking about. So let's say you have this table accounts that has 3 fields. The Spark application is going to ask where this table is to the Hive Metastore server, is going to return the path to that table in the file system. And the user code goes directly to HDFS and asks for the files in the accounts directory. And basically, the file system returns the files with all the data. So if the user doesn't have access to one of those fields, there's no way to do that filtering here. So in the future, we at Cloudera believe the way to fix this is to use record service. Record service is a distributed service to access structured data. It basically it follows the same pattern as, for example, HDFS, where you have a central node that knows about where the data is. And it works as a drop-in replacement to Hive input format. So instead of reading data using Hive classes, you use the record service version of those classes, and you're going to be talking to the record service daemons to fetch the data. It integrates with Spark SQL data sources API. So there's no direct dependency on the record service API in your applications. You just tell this table is a record service table, and Spark SQL knows what to do with it. And it supports things like predicate pushdown and projections efficiently. So what am I talking about when I talk about row level and column level permissions? So one way of doing that, for example, is with views. Looking at our previous table, let's say that you want to create a view customers where you're only allowed to see the customer name and the country the customer is from. So if you query that view, you will not have access to the balance of the customers. And let's say that you want some department to only see data from customers in the US. So you create this other view that only returns data from customers that are based on the US. So if you go back to our example, now it's slightly modified. Instead of talking to the Metastore server and HDFS directly, now you're going to be talking to record service. The Metastore server is replaced by the record service planner. And basically now your code goes and asks where is table accounts, and the record service planner may decide you can't read it, you don't have access permissions to that table. So if you remember the views from the previous slide, now let's say that the user has access to the customer's view that you created. So you can ask where is the customer's table. And the planner returns and says, go look at this other, go talk to this worker who knows where the data is. So basically the worker is like the data node in HDFS. So your user now goes and asks for the table data from the worker. And instead of returning the file with all of the data, now the worker knows that the user code only can see those fields because that's how you define the view. And it returns only the data that the user can see. So no sensitive data that the user should not look at is ever returned to the user in this scenario. To finish up, so Spark can be made secure today. There are a few kinks that are left to fix, but all the infrastructure is there. It builds on top of the security features of Hadoop. So if you don't use secure Hadoop today, do that first, and then start thinking about securing Spark. There's still some work to be done. Using stronger encryption algorithms is one of them. Figuring out a way to make SSL easier to use for those who really care about protecting the web UI. And also better integration with Sentry and record service so that all this data that's stored in Hive today can be properly shared with Spark applications. And for those looking for some references, there are some bugs tracking the encryption work in Spark, delegation tokens, and some links to Sentry and record service. Record service just had a new beta release last week, I believe, the 3rd beta release. So if you want to try it out, this is a good time. And that's it. Thanks a lot for coming, and I'll take question now. Oh, sure.
About the token application limitation of 7 days?
Yes.
There is any workaround?
I believe there is a setting that you can use to increase that value or disable it. But other than that, right now, if you're using Spark, the only workaround is to provide your Kerberos credentials, basically your principal and your key tab name, and Spark will renew your HDFS tokens, but nothing else. If you're using anything that's not HDFS, you have to restart the application after the period.
Do you know when it's going to be fixed?
When it's going to be fixed, I don't believe there's currently any ongoing work. We definitely want to take a look at it, but it requires some more thinking, especially because things like Kafka are going to come into the picture. So it's better to fix it in a way that can be fixed for all the applications at the same time.
With Spark standalone, it's much simpler now to get it the security, at least the wire security. It's just setting a property, right? Spark standalone. When if you don't use
for just encryption on the wire. Yeah, it's a single property for all the different backends. It's a single property for Yarn also and for Mesos. The difference here is that Yarn is really the only secure way of setting up encryption. For Spark standalone, for example, it requires the secret used to create the key for encryption should be shared among all applications. Yarn is the only backend in Spark right now that creates a separate key for each application, and that's what really makes it secure.
No, it's the same key for all the applications, shared key with Spark standalone, or can you create a different key for each one?
Right now, it's the same for everyone.
Yeah, okay.
Yeah. So it would protect you from external people just sniffing your traffic, but not protect applications from each other. All right. Thanks a lot for coming.